Okay, yesterday, or last day I should say, we built one of these. Do you remember building one of these?
Yeah.
And do you remember having, I can't remember which cup I drew it on the board, but I'll just write, iron sulfate, so Fe2 plus and SO4 2 minus, and lead nitrate, so Pb2 plus and NO3 minus. Do you remember having that?
Yeah.
And do you remember seeing a white solid precipitate formed for some of you?
Yeah.
So the white solid precipitate formed, I'm pretty sure, is PbSO4 solid. So where must the so at some point, the Pb2 plus and the SO4 2 minus must have come into contact with each other. But one's in one beaker and the other's in the other beaker. Aha. Okay. So what's the only pathway, logically? That's right, the U-tube. So the job of the U-tube is to allow ions to flow. The reason we need ions to flow is to complete our circuit. Like in physics, I'm not changing it, you learned you had to have a complete circuit in order for the light bulb to turn on. Well, this is the same thing. If we had, oops, there are my sticks, and then you had a wire and a voltmeter, and the voltmeter said, ha-ha, we have electricity, right? So if we had a light bulb there, it would have shone. And so where must that electricity be coming from? Well, here we made a battery, if you remember. But you have to have a complete circuit. And so what is completing the circuit? Those ions are carrying the charge. Just like they did when you learned what's an electrolyte and how does it work in Chem 20 and Science 10. You learned that the ions are free to flow and that's why you can have it. So the ions must be flowing through here. And that's how we complete the circuit. Does that make sense? So today we're going to look at the voltaic cell and exactly how it works and exactly what's flowing where. And it's going to look like one giant big essay when we're done. All right? And in that little system, I should be able to say, oh, this part, and then you work the rest out. Or, oh, this part, and then you work the rest out. And that's how they give you a little bit of information and you put the rest of the essay together. That's how these questions come alive. Okay, this is another example of taking your two half cells. The reason we have to have two half cells is so that you can say, oh, look, white precipitate. Oh, which one moved where? Okay? And you can say, oh, look, this electrode is decreasing a mass. Oh, what must be the strongest oxidizing agent? So in order for us to study what's happening, we have to keep the two things separate from each other. Otherwise, you'll just have a little spontaneous reaction happening here. And you won't have a flow of electrons. So at the very beginning of chapter 12, you had spontaneous reactions happening. Right? You reacted things together. You had a spontaneous reaction, for example, most recently in your titration. It was a spontaneous reaction happening in your conical flask, or Erlenmeyer flask. There's no wire. There's no electricity. So in order to have the current flow, we have to separate them. So they're forced to go along this pathway. If I threw these things together, the electrons would just be transferred down in there. And I wouldn't be able to get electricity out of it. So one thing that Voltaic did when he was designing his cells is he separated the two half cells to force the electrons to travel on a pathway so that we can use them. Does that make sense? So another way of separating the two is this porous cup. So here's a porous cup. Passed around. It really honestly just, porous as in ceramic, as in a coffee mug. But think of raw ceramic. So it's clay that's been put together. So if I pour some liquid into it, the liquid will stay in there. And the next one you design, you'll design with this. The liquid will stay in the cup. Everybody okay with that? And if I put that cup in a bigger cup, the liquid will stay in this cup. But yet the pores are big enough that the ions can still go across. So it's just a little bit more kind of compact than having the U-tube. Okay, and that's what they do in batteries. They have a little porous membrane that separates the two half cells. So this looks more like a Duracell battery all of a sudden, as opposed to that one. Everybody okay with that? Okay. So today we're going to look, at some more half cells. I've got a copper zinc voltaic cell here. Just a reminder, voltaic cell. What did voltaic cell mean? Right, it's a battery. What else? Spontaneous. And therefore it produces a voltage. Okay? It is a battery, it is spontaneous, produces a voltage. And yes, I would write that down too, Gabby. Fancy that. At least you're on the right page. Okay. So I've drawn this little system for you in your package, and you see I've got a copper electrode.
Junior class change.
What's an electrode again? That was a definition on our very first package, or first page, I mean, maybe second page. An electrode, it's a solid conductor. Did somebody say that back there? Good job. Well, you didn't just guess, you pulled it out of that memory of yours. So it's a solid conductor. So most often it's a metal, but can anybody think of a solid conductor that's not a metal? It's a metal. And it's not solid. A solid conductor.
Think of what?
A conductor, something that conducts electricity, but it's not a metal. Back in junior high. Graphite? Carbon? Okay. So carbon, graphite is another electrode that's not a metal. Okay? So you can't define electrode as a metal, all right? But they most often are. Here's another solid electrode. Here I have zinc for my electrode. And my electrolyte, oh, what's the definition of an electrolyte? An aqueous, pardon? An aqueous or liquid that conducts electricity. Good. So here's some aqueous solutions that conduct electricity. Here I have copper nitrate. Here I have zinc nitrate. And in my salt bridge, I need to have either the same as one of these solutions or something that won't react. Something that's so low in the species list that it won't be a strongest of anything. So here I've got some sodium nitrate because we all know Na plus and NO3 minus are both very low on the reactivity. Okay? So you're choosing something you would want to be a spectator ion. Okay, now how great is it to draw these over and over again? Not at all. So of course we have this cell notation which helps us visualize this but not have to draw it. And it looks like this. Symbol, line, symbol, double line. Symbol, line, symbol. Okay? Where the copper and the zinc on the outsides are the electrodes on the outsides. You see that? And the single line separates the electrode and the electrolyte. So electrode, line, electrolyte. So this electrode is stuck into this solution. Everybody okay with that? And the double line indicates a porous boundary. So a salt bridge or the porous cup or who cares, they're separated. And then I've got this solution in a beaker and this stick is stuck into that solution. Everybody get cell notation? And it has to be in this order. Electrode, electrolyte, double line. Electrolyte, electrode.
Does it matter what side it's on though?
It doesn't matter. That's a really tough question actually for me to answer. So I've written it this way because as a teacher I want you to see how this is related to this. Right? But I could have written it this way. Zinc, zinc nitrate, copper nitrate, copper. Because actually if I build this and you're in Mr. Moore's room and you're looking at it, what's on my left is on your right and what's on your right is on my left. So the way I write it doesn't matter. Does that make sense? And so there's actually a proper cell notation method And it talks about how you should write the anode first. This is the anode. And the cathode second. This is the cathode. But at this point in the lesson, you don't know what cathode and anode are. Okay? So we'll just pause on that too. But the reason I wrote it this way is so you could see they look the same. They are the same. But you don't have to write it in this order. And sometimes when they give it to you, it's not in proper cell notation either. So, okay. All right? Yep. Okay, moving on. So let's talk about what's happening here. In fact, it's all sort of later on in the package, but I'd like to keep this page of this board up. When you have a bunch of this stuff happening, and they all can flow to the other thing, we already talked about that, how we've got an ability to flow here, right? That I could flow through the wire. What flows through the wire?
Charge.
Electrons. Electrons flow through the wire. Remember that from the first page? Mm-hmm. And the ions can flow through the bridge. So, in essence, everything's mixed. Or able to mix, anyway. Able to come in contact. So just like we did last chapter, we're going to list our species. And we're going to find our strongest. And we're going to find our strongest. Okay, so let's just do that. So we're listing our species. We've got copper, we've got copper 2+, we've got nitrate, we've got zinc 2+, and we've got zinc. Oh yeah, we've got water, but you know water's so weak that it's not going to play a part. Okay, you know water's so weak it's not going to play a part, so I don't even bother. It's there, I know it's there. You can write it down if you like. Anyway, go and find your strongest and strongest and tell me what you get. Oh yeah, I've got this as well, you know. I know it's not going to play a part either. And more N nitrate. And Na+. Okay, but it's going to not be that. It's going to be a spectator. Na plus?
No, Na.
Do I have Na solid? No, I don't. Graham, what'd you find? Yep, either one. Or both. The zinc ion or the zinc solid? Solid. And the strongest oxidizing agent?
Would be Cu2+.
True. The Cu2+. Everybody okay? So in this copper zinc battery, it's the zinc that's our strongest reducing agent, and our copper, the copper 2+, that's our strongest oxidizing agent. And what did I do last chapter? After I found my strongest, wrote down the half reactions as per the data booklet. So zinc is going to go into zinc 2+ and 2 electrons, and copper 2+ will be gaining 2 electrons to become copper. Everybody okay with that? Just make sure that's still in the board. Yep. And then I balance the electrons. Oh, good. 2 and 2. Easy. And I could write my net. Zinc plus copper 2+ goes to copper plus zinc 2+. Are you okay with that? And this guy is losing electrons, oxidation, and this guy is gaining electrons, reduction. So far, so good? Okay. So in chapter 12, we learned that Leo, the lion, says grr. And that oxidation reactions are done by the reducing agent. And that reduction reactions are done by the oxidizing agent. Okay? So now instead of Leo, the lion, saying grr, you're going to memorize that Leoa, the lioness, says grr. And at the anode, that's where this happens. the oxidation reaction. And at the cathode, that's where this happens, the reduction reaction. So reduction takes place at the cathode, GERC, and oxidation takes place at the anode, which is your LIOA. Gabby, write those two sentences down.
Oh yeah, I know. I used to sling in my eye.
Okay, everybody? So, on our picture, which is the anode, which is the cathode? The anode is zinc, right? So therefore, the zinc is the anode. And this is the cathode. Everybody okay with that? Okay. Now, the zinc is reacting. It's a reactant. It's being used up. And so the zinc will eventually be depleted. Everybody get that? And so the zinc is reacting and it is forming Zn2+. So the concentration of Zn2 pluses are increasing here because it's already got zinc nitrate. So it's just got now more Zn2 pluses. So its concentration is increasing. And the 2 electrons are going where? In the wire. Electrons travel down the wire. So Zn, for every 1 Zn that is depleted, I have a Zn2 plus that's made and 2 electrons. Or for every 1 mole of mass that it's decreased, I have 1 mole of Zn2 plus, concentration increase, and 2 moles of electrons. Because 1 to 1 to 2, mole ratio, 1 to 1 to 2. Just like science 10. Okay? Okay, so 2 electrons go through the wire. Oh, they're going through the wire. Oh, they're going through the wire. Oh, they go through the wire. Oh, and up here I have a buildup of electrons. All right. What charge? Oh, wait, hold on. On our very first page, we talked about how electrons flow from the anode to the cathode. Is that what's happening? Oh, so that agrees. So electrons flow through the wire from the anode to the cathode. Electrons flow through the wire from the anode to the cathode. Everybody okay? Okay. This board doesn't quite fit in this thing, but that's okay. What charge do you think the cathode must have? Why do you think negative, Davin? What's building up there? Electrons. What charge are electrons? Negative. So it has an excess of negative hanging out there. So therefore, it must be the negative terminal of our battery. So cathodes are negative because, in voltaic cells, because I have a buildup of electrons there. Because the wires are, the electrons, I mean, are leaving that, going through the wire and building up there. And so when I hook this battery up, I'm going to take something and clip it to there and attach it to a light bulb or whatever. That must be the negative post. Okay? The anode is positive because, you could say because the electrons are leaving. therefore it's positive. You could say because you've got Zn2 pluses, therefore it's positive.
So
Okay.
it wants to lose them because it wants to become neutral. So it gives them away.
No. Why is the Zn losing electrons? The Zn is losing electrons because it is our strongest reducing agent. And therefore it is the most keen to become Zn2 plus. More keen than the copper is to become copper 2 plus. So it wins. No. I'm going to lose my electrons before you. Okay? They both want to become ions to become more stable, but zinc wants it more. Okay. Everybody okay with that? Alright, so the zinc is losing mass. It's doing this. It's becoming that. And 2 electrons. The electrons are going over here. The electrons are building up over there. What might be attracted to this negative area of many electrons? What might be attracted to the negative area of many electrons?
Something positive.
Something positive. Can you find something positive for me?
Na plus.
Na plus. Okay, so here's my Na pluses. Which direction do you think they're going to move? That's right, to the cathode. What else is moving towards that negative area? What other positives? Zn. 2 pluses. These Zn2 pluses, how are they going to get all the way over to the cathode?
Through the U-tube.
Oh, through the U-tube. So Zn2 pluses are traveling this way as well. And the third? The copper 2 pluses, which are already here-ish, are going to move there. So who's hanging out here? I've got copper 2 pluses, I've got sodium pluses, I've got zinc 2 pluses. They're all able to gain these electrons. Who wins? The strongest one wins. Who's the strongest one to gain electrons, or the strongest one to be reduced, or the strongest oxidizing agent? Just said the same thing 5 times. Whoop. The strongest oxidizing agent? The copper 2 plus. Out of all the species, see this is just a species list. Out of the species list here, the copper 2 plus is the strongest, so it will gain those 2 electrons. And what does it become? According to chapter 12? More copper. So the mass of this post should increase. The mass of that electrode will increase as more copper is made.
So all of those, like the Na and zinc, also turn into their elements?
Not while the copper's there.
No. Okay.
If all the copper's gone, which won't happen,
Okay.
but if it did, then the next order, the next person to win this battle would be zinc 2 plus because it's the second strongest. And then after all the zinc 2 plus is gone, then I'm going to have the sodium.
So then all your NO3 just goes to the other.
Okay, so good. So if I've got my, oh, by the way, that means we could write here, the cation ions, those are the positively charged ions, right? Move towards the, where? Cathode. Did you see all the cations moving to the cathode? Why? Because the cathode is negative, and they're attracted. So, we've got a lot of statements here. Electrons flow through the wire from the anode to the cathode. Reduction takes place at the cathode. Oxidation takes place at the anode. Cations move towards the cathode. And then Nick's just made an observation. Hey, what about those anions, which are negatively charged? What anions have I got? NO3 minuses. I've got them everywhere, but I only have NO3 minuses. Wouldn't they be attracted to the positive anode? Okay, so anions will move towards the anode, which is positive. that make sense? And so that's the whole, that's the whole essay. That's the whole story. And it's a circle. Everything's connected, everything's linked together. And I should be able to give you one piece of that puzzle, and then off you go. For example, if I said, the electrons are flowing this way. Oh, well then you know that's the anode, and this is the cathode. And if you know this is the anode, you know it's LiOA. And if you know it's LiOA, it must be losing electrons. If you know it's losing electrons, you know this post must be decreasing in mass. So just by the flow of electrons, you should be able to tell me which post will decrease in mass. Right? If the electrons are flowing this way, which direction are the anions flowing? Well, the electrons are this way, so therefore that's anode, that's cathode. Therefore the anions flow towards the anode, so the anions go in that direction. See how I could, same beginning, but different question. I could give you another beginning. If this mass is increasing, okay, that mass is increasing, I must be taking the ion and making a solid. So therefore this is GERC, therefore this is the cathode. Which direction are the electrons then? Oh, anode to cathode, that direction. So I can give you one piece of the story and you should be able to puzzle the rest together. But you kind of have to know the full thing in order to do it. Does that make sense? Questions on that before I just cover the last bit of these pages? Okay, so a couple loose ends to tidy up before... So here I've said proper cell notation, we would write anode on the left, double line cathode on the right. Everybody okay with that? Here I've talked about which solid is depleted, where the electrons are flowing. Basically that little chicken scratch there, this was space for you to write all of that, but we wrote it up with a picture because I thought that felt better. LiOA and GERC, we already covered that. The electrons released, we covered that. Here they react with the Cu2 plus ions to produce more copper, we already covered that. There's your species list. Oh, so here's another way of writing the cell notation. What have I taken out? Taken out the NO3 minus. Why was I allowed to do that?
So you're showcasing what it changes.
Right, I'm just showcasing the actual players, not the spectators. So I've taken the spectator ions out.
So do you care which way we write it? Like that way or the other way?
Not unless I say proper notation. Okay? Oh, you mean like with or without the spectators? Yeah. No, but you have to be able to read it both ways. Okay? All other entities can be assumed to be spectator ions, right? So, oh yeah, what's the voltage of this cell? We said it was a voltaic cell, therefore it's spontaneous, therefore it should produce a voltage. Do you remember how to do that? We have to look up the voltage on the zinc and look up the voltage on the copper. Well, the zinc, according to this sheet, is 0.76, but it's negative in your data booklet. Right? But I'm writing it flipped, so what do I do to the sign? Flip it. And then I can add them just like, so this is just like my delta H now. Writing the reaction, writing the delta H, flip it, flip the sign, add it if I'm adding those two half reactions. Okay? And I get positive 1.10 volts in this battery. Everybody happy with that? Okay. There's a much faster way. So let's say I just said, hey, look at this pretty picture up here. Look at it. It's so pretty. What's the voltage on this cell? No information, no half reactions. I told you it's copper and zinc. What's the voltage? Well, you could list your species, find your strongest, write that half reactions, flip, flip, add, and you'll get the right answer. Or you can look in your data booklet, figure out which is which, know that this is going to be the GERC, and this is going to be the LiOA, because reducing agent oxidation. And then we're going to go cathode minus anode. So you go, what is it, positive 0.34
Yeah.
minus negative 0.76, or whatever my memory is telling me. And therefore, that's still 1.1 volts. So that's the fast way, so you don't have to write your half reactions down. And by the way, your cathode's always the top value. So it's always the top minus the second one that you found on the bottom, and then you get your voltage on that column of voltages. Oh, way faster. Does that make sense? Okay. So that was another loose end to tidy up. I think that was the last one. Oh, inert electrode. Okay. So, what does inert mean? This is the last loose end to tidy up, I promise. What's inert mean? If something is inert. Inert. I-N-E-R-T.
It's neither.
Gabby,
I don't want to say
you're a
it's fine.
linguist. What do you think?
No, it's fine.
Okay. What's inert?
Bottom of this picture.
I was scared I'm wrong, so. Doing anything?
Not doing anything.
Oh, I was actually right.
Not doing anything. So inert means non-reactive. Okay? It doesn't, it's not. So going up here to our pretty picture again. Do you notice that this post, its only job is to have the electrons travel down it. That's its only job. I could put any conductor in there. If I took that piece of copper out and I put in a piece of carbon graphite, it would still do the same job. Because over here, when I'm listing it and I put carbon instead, it still wouldn't be my strongest. And the carbon graphite would still allow the electrons to flow down. And the carbon graphite would still allow the copper to be plated on it. And now I'd have copper-plated carbon. So a carbon with a layer of copper on the outside. Would maybe look a lot nicer if I put a coin there. Oh, okay, well let's dip a coin there instead and hook my wire up to the coin and have the coin dipped in the solution. And now my coin will have copper plated on it. Does that make sense? Because it's inert. It itself doesn't react. It doesn't matter what it is, as long as it can conduct electricity. Okay? So, not necessarily never reactive, but in this setup, it doesn't react. So you always have one inert electrode. Not always. You often have one inert electrode. Okay. I'm done. Now time for you to practice all that. And it does take some practice to get your head around it. So here I have some textbook questions for you to work on. Blah, 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 blah. That'll help. And here I have a sheet, or for the hitmen who are on the road, you guys can do your snap booklet questions. And here I have the voltaic cells sheet as well.
Jason's class.
Other.
Oh, I was like that.
Okay?